Good morning, friends. Welcome to Water Resources Engineering class. So we are dealing with hydrology. Part 1 we have completed, and in part 2 we are right now. In the part 2 portion, we have already completed the evaporation process. Evaporometers we have completed, and in today's class we will deal these two things. Analytical methods of evaporation estimation, reservoir evaporation and methods for its reduction. Before going to that, I wish to just solve a problem on evaporometers actually. Here, if you look into this problem, the monthly pan evaporation data near Chilika Lake in 2023 is tabulated below. At the beginning of January, the water spread area is 1,165 kilometers square, while at the end of the December, the water spread area reduced to 906 kilometers square. Calculate the volume of evaporation water loss, assuming the pan coefficient as 0.75. So the pan evaporation data is with us for that 1 year, starting from January to December. In terms of in mm, he has given us this. Suppose if you take at the beginning of January, what is the water spread area? So water spread area is 1,165 kilometers square. At the end of the December, it is 906 kilometers square. So what is the average water spread area? Beginning is 1165, ending is 906. So what is the average? So this average, if you see any lake like the lake, basically if it's of almost irregular cross section. But if I want to calculate the average, I need to follow some guideline. So that guideline is we have used trapezoidal formula for calculating the average area. So what is trapezoidal formula? It is 1/3 of A1 plus A2 plus square root of A1 A2. Applied the same thing, and I got the average area, water spread area is 1032.79 kilometers square. So now what is the total pan evaporation? Sum up all the things. So it is 2400 mm. Please look at the units. Units are very, very, very important. So total evaporation during the year is 2410. And pan coefficient is already given 0.75. So what is the lake evaporation? Lake evaporation is equal to pan evaporation multiplied by pan coefficient. So it is 1807.5 mm. So we got that. Now what is my job? I got this is in terms of depth unit. This is in terms of area unit. So this is in area unit. This is in depth unit. So how can I get the volume? Area multiplied by the depth. So if I do that, then naturally, so this if you take it 1032.79 into 0.6 into the area, if I put it, lake evaporation is this, and this is the average area. So while writing what is 10 to the power of 6, what it represents, the 10 to the power of 6 represents from kilometer square to meter square. 1000 into 1000, so 10 to the power of 6. Why 10 to the power of minus 3? It is in mm, so I converted into meters. Now this is also in meters, this is also in meters. So finally what we get is in meters. So 10 to the power of 6 is nothing but actually what it represents, 10 to the power of 6 represents actually 1 million. So that's why we have written 1866.77 million meter cube. So this is what is the answer. So what is given? Evaporation data is given. We converted into evaporation depth. Then from there lake evaporation we have calculated. After calculating the lake evaporation, what is the water spread area, average water spread area, that we calculated. Multiplying both the things, we got the solution for what is the volume of evaporation. Then what are the empirical equations? Because we mentioned at the beginning itself, evaporometers is one solution, empirical methods is another solution, analytical methods is the third solution for calculating the evaporation. So evaporometers we have completed. So after the evaporometers, next one is empirical equation. So this empirical equation is given by Mayer actually, wherein evaporation is equal to Km into Es minus Ea into 1 plus V9 by 16. What each term represents. E is evaporation per day, right, in terms of mm. What is Es? It is the saturation vapor pressure at the water surface. Please note that saturation vapor pressure at the water surface temperature. What is the Ea? Actual vapor pressure above the water surface actually at a specified height. What is V9? 9 indicates 9 meters above the ground. So mean monthly velocity, this is nothing but to take care of into the wind velocity. Mean monthly velocity above 9 meters from the ground level, that is V9. What is Km? Km is nothing but the coefficient accounting for other factors depending upon whether the lake is a shallow lake, whether the lake is a deep lake actually. Based on those things, naturally this Km is calculated. So Km is the coefficient, Es is the saturation vapor pressure on the water surface, Ea is the actual vapor pressure above the water surface at a specified height, V9 is the wind velocity or velocity of the wind at 9 meters above the ground level. So using this formula, we can calculate what is the evaporation. Similarly, Rover's formula is another formula actually. It is also same actually, but it mostly depends on, again, the wind velocity is one aspect, again the barometric pressure is one aspect, and again saturation vapor pressure and actual vapor pressure. On these 4 points it depends on, and in that also if you see what is V.6 is, it is the mean wind velocity in kilometers per hour at 0.6 meters above the ground level. So that is what is mean by V.6. What is PA? What is the mean average barometric pressure? That is what we call it as PA. And EA already I explained. And naturally, how to get the wind velocity at any height? Wind velocity is equal to C into H to the power of 1 by 7. The wind velocity is given up to 500 meters above the ground level. The wind velocity is always given by 1/7 power law. So it is C into H to the power of 1 by 7, where C is a constant. H is the height above the ground level. Based on that, VH can be obtained, and that which we can substitute in the equation. So this is another formula which we call it as Rover's formula, right? After Rover's formula, then we go for analytical methods. What are the analytical methods? Analytical methods is, first one is the water budget method or water balance method, which is a very popular method also, which mostly we will use this method. So in this, what is simple, I will tell. What is this water balance method is, what is the inflow into the reservoir, right? Wherever you want to find out the evaporation, what is the inflow into it? What is the outflow from it? What is the change in storage in that? And then evaporation loss. So these are the 4 things. So inflow will be there, outflow will be there, evaporation will be there, then naturally some change in storage maybe because of the seepage. So these are the 4 things that are possible. So that's what we have written. Inflow minus outflow is equal to change in storage plus evaporation. Therefore, evaporation is equal to, it is basically inflow minus outflow plus or minus delta S. Then if you want to generalize that equation, then inflow, what is that inflow? I am telling. The evaporation is equal, all this term becomes the inflow. What is that inflow? Inflow means actually whatever is the surface runoff that is coming, surface flow that is coming into the reservoir. This is what is that. Second one is any rainfall is there in the reservoir. That is number 2. And what is the groundwater? Any groundwater also is adding as inflow. So that is 3. What is outflow? Outflow is whatever is the surface outflow from the thing. From any canal water we are sending it, that is outflow. And what is outflow into the groundwater? that is nothing but seepage actually, and transpiration. If anything is there, which is any plants are there, from there any transpiration is there, that is the next one. On the banks or on the only on the lake itself, if suppose some plants are there, floating plants, from there any water loss is there from the plant, that is transpiration. And delta S, this is it. So final conclusion is, I remove all the things. Evaporation is equal to, please note it, inflow means whatever is the surface inflow plus precipitation. That's all. Outflow means whatever is going from the reservoir. One OS means whatever is the seepage. If any seepage is there into the from the reservoir, that is major component. Last one is change in storage. If any change in storage is there, that should be taken. So if you can do that, that will be fine. Now I will show you with a problem. A 100-hectare reservoir receives 2500 mm of rainfall during a period of 2 years. During this period, the mean inflow into the stream is 1 cubic. The mean outflow is 0.8 cubic. And increase in storage is 500 mm. Assuming that there is no seepage loss, calculate the total evaporation. Let us see. What is cubic first? Once again, please note it. Cubic means meter cube per second. Cusec means cubic feet per second. So these are the common discharge units that are being utilized in irrigation. So cubic means 1 meter cube per second. What is hectare? Hectare means actually 10 to the power of 4 meters square. Hectare is something related to the area, right? So 1 hectare is equal to 10 to the power of 4 meters square. That is the thing. Then what is million actually? Million means what? Million is equal to 10 to the power of 6. So these three kindly please first understand, then naturally I will take up the problem afterwards. So now what I will take? What is the rainfall? Please see it. Rainfall is 2500 mm. That's what I have written. What is the reservoir area? Only somewhere 100 hectares. So 100 hectares is equal to 100 into 10 to the power of 4 square meters. So that means what it will be 10 to the power of 6 meter cube. 10 to the power of 6 meter cube means what? 1 million meter cube. That's what I have written here. Then what is the total volume of rainfall? Depth into area. So depth is how much? 2500 mm. If I convert into meters, 2500 into 10 to the power of -3. And what is the area? 1 million. So finally answer is 2.5 million meter cube. Then what is the time period they have given? 2 years. Now what is the inflow? This is all whatever you have calculated till now, all this related to precipitation. Precipitation is also inflow, please note it. Then what is the inflow? Inflow he has given in terms of what? 1 meter, 1 cubic. 1 cubic means 1 meter cube per second. But how much time he has given? 2 years. Per second, 1 meter cube of water is entering into the reservoir. So per 2 years, how much water will enter into the reservoir? That's what I have taken. So 1 into 2 years. 2 years means 2 years. Into per year, days how many? 365. Per day how many hours? 24. Per hour how many minutes? 60. Per minute how many seconds? 60. So all multiplied, we got what is the total inflow. Similarly, total outflow also we calculate. Change in storage also he has given. How much he has given? 500 hectare meters. That means 500 into 10 to the power of 4. 2 zeros also come here, 5 into 10 to the power. So 5 million cubic meter. Seepage loss, what he mentioned? 0. So what is the water budget equation? Evaporation is equal to total inflow. Total inflow means what? Inflow plus precipitation minus total outflow minus change in storage minus seepage. So seepage anyhow he has given it as 0. Change in storage is how much? 5 million meter cube. Right? Total outflow we got it. Total rainfall already known. Total inflow known. I have substituted it. So the total evaporation is this much. Then what should I find evaporation in terms of depth units? So what is the area? Area is nothing but 1 million meter cube. That's what I have put. So this is mm. Now you imagine how much, Andy? Please just see how much is the evaporation loss. If you see, that means 10,114 mm. So if you convert into meters, actually 10.114 meters of water is evaporated. Now you see how much is that quantity, and you see how much 10.1 million meter cube is lost due to evaporation. So that's why evaporation is such a great loss from any reservoir. That is what I want to emphasize. Similarly, energy budget equation or energy balance equation. So again, here what I will do, rather previously what water budget means, inflow, outflow, storage. These are the 2-3 things I have taken. Here what I will take it, conservation of energy, how the energy is coming, how the energy is going out, and finally what is the final thing actually. So incoming energy, outgoing energy, stored energy. These 3 things we put it in the form of equation. What is net heat energy? First one is equal to, net heat energy is equal to, so Hc into 1 minus R minus Hp. So these are all basically how much is the incoming solar radiation into the surface. So that is what the first one. What is Hp means? What is the outgoing reflection out of it? So that is the thing. So if you see, Hb is the back radiation and Hc into 1 minus R is the incoming radiation. So if you remove one minus the other, will give you the net energy. Then sensible heat transfer from water surface to air. Then heat energy used in evaporation, right? And then what is the heat flux into the ground, into seepage like, and what is the net heat conducted out of the system by water flow, outflow. What is the heat stored in water body, and latent heat of evaporation. These are all related to the energy terms. In the above equation, all the energy terms are in calories per square mm per day. All the terms except HA, all the terms except HA can either be measured or evaluated. For small time period, HS and HI, this HS and HI both can be neglected. However, because now still our problem is not solved, only we have find out actually what is the net heat energy. After that, actually what the sensible heat term H can be estimated by using Bowen's ratio, which is given by B is equal to HA divided by rho W into LA into E, where rho W is nothing but density and LA is nothing but latent, basically that is what we call it as latent heat, and E is the evaporation. So from those two equations, we can find out E, that is the next thing. So these are the two methods, analytical method. One is the water budget method, then second one is the energy budget method. One is the inflow outflow business, second one is the incoming energy, outgoing energy and stored energy. So based on the energy and based on that which we can do it. Then next our issue is how to reduce evaporation from the reservoirs. Because just now I showed to you with a problem that how much is the amount of water lost through evaporation. It's a huge quantity. So that how to reduce that, that is one of the important parameters. Because problem is reservoir is such a large area, even though we speak different methods, these methods may work out for small reservoirs but not bigger reservoirs. So first thing is reducing the surface area. So whenever you are creating a lake, whenever you are creating a reservoir, kindly remember that the surface area has to be reduced. If the less surface area, then naturally lesser the evaporation. So deeper the thing, lesser the evaporation. So always you prefer to go for a deep reservoir rather than a shallow reservoir. A shallow reservoir occupies more surface area, because of which the evaporation loss will be very high. Whereas if you go for a deep reservoir, the surface area will be less. For the given volume, automatically the evaporation will be less. So that is what the first point is. Reducing the surface area while creating a reservoir or a lake or a pond, that shall be the one of the criteria for reducing evaporation. What is the next one? Continuous floating covers. So we take polythene covers, plastic covers, and we allow them to float on the entire water surface. The entire water spread area is covered with plastic covers, floating covers. Because of that, probably evaporation you can really definitely reduce it. But the problem is very high initial capital cost. How much cost actually involved in that? How to make them to stand at the surface and a tying mechanism. So all that will be initial cost is very, very high. And second thing is whether this plastic sheet is going to impact the water quality. That is also we have to check, because when you are covering the whole thing, the dissolved oxygen levels will change. Whether that is going to really do anything with respect to water quality reduction, that is one of the concerns actually. Then main thing is how to keep these floating covers. That is basically the structural integrity of the product under windy conditions. If suppose the winds are blowing, how it is stable actually. And similarly, water levels may be fluctuating in the reservoir. Will this floating cover will be able to withstand for that? These are some of the issues. Then modular covers. To overcome that difficulty of the previous one, floating covers, modular covers. Modular covers means the size of the plastic cover is less. That means we have taken different plastic covers and try to really make them arranged on the water surface of the reservoir. So each, for example, we are taking a 3 meter square area, each of the plastic sheet, a square sheet or a rectangular sheet, and then we are putting it. But again, the problem is to keep all these covers intact. The mechanism that usually require is the cost of that mechanism is very, very high. That is the thing. So this is second thing actually. So instead of going for complete one floating cover on the entire reservoir, you make different sheets, each of 3 meter square area, and then again allow it to float. Not only that, wherever you feel that evaporation losses can be very high, at that places you can cover, not all the things. So this is a little bit advantageous compared to the previous one, but still the problem remains, high capital cost still remains, quality has to be answered. Then shade structures. Suppose if you construct a shade, for example, from the bank onto the reservoir, some dome type structures if you are creating, then in such a case also you can really stop that means you can really arrest the sun's radiation to some extent, thereby actually evaporation losses can be reduced. But constructing such a shade structure around the reservoir, making shades into the reservoir, thereby the only exposure that is being given is minimal if you can do it, but that reduces evaporation, but it is definitely a high initial investment. So it all depends on cost versus the benefit that is to be calculated in any reservoir. Then one more thing is, this is one of the popular things in Australia reservoirs. So chemical covers are surface films. So what we do is we take a chemical actually, and that we spread that chemical on the surface of the water actually. So the chemicals will be such that it will not affect the quality of water. So the chemical acts like a film on the surface, thereby it reduces the temperature, thereby actually naturally the evaporation losses are going to be minimal. The chemicals are also such that they are all biodegradable chemicals only, so that's why they may not affect much into the water quality, which is the chemical that is very popular actually which is spread on the reservoir surface area is hexadecanol. Hexadecanol is the chemical that is being sprayed on the reservoir water surface to reduce evaporation. The same thing is also called as cetyl alcohol. Hexadecanol is the chemical that is being used for reducing the evaporation. So this completes to me the evaporation topic actually. So we have completed the evaporation topic in 2 lectures. So thank you very much for your patient listening into it. Thank you.
Vishnu Audio Visual Center, like and share and subscribe and click bell icon.